very much. And because of COVID years, the continuation of my progress in 2000. Yeah, okay. Yeah, in the meantime, it was a great progress by Hiroshi Ritani, this law of formula, and now we can do arithmetics. So, what is the kind of underlying thing? From the early days of Gromov-Peterson invariance, Gromov-Peterson theory, it had two flavors. It was part of symplectic geometry, and it was part of algebraic geometry. So those are, of course, they're compatible with that variety of complex numbers, which is scalar manifold, symplectic manifold. It should be kind of the same numbers, but in the algebraic geometry you get more fine invariance. And yeah, I think it's Yuri Manin also was very fascinated by this duality of the stories of motives, mirror symmetry, together. And I will discuss what are correlates of algebraic geometry from Gromov-Peterson theory. And the real interesting color is not how many curves of degree 10 and 5 dimensions involved, of huge numbers, but it will be actual application to very classical equations of variation algebraic geometry. First of all, just I want to start with the thing I want to say that these days Gromov-Peterson invariance can be defined in very big generality. We have varieties over any field, would be positive characteristic. Okay. Yeah, that will be a variety of any characteristic. This story is completely unchaptered. For example, imagine Calabi-Yosef default over a field of characteristic P, which cannot be characteristic 0. So we have no tools to calculate Gromov-Peterson invariance through zero characteristic methods, and nobody has any idea what will be generated series. But I will use resolution singularity. So in my lectures, I will stick to characteristic 0, and then I can relate with neutral geometry. But important point that Gromov-Peterson invariance can really go fine even when case complex numbers. More fine algebraic geometry is more fine than symplectic geometry. And let me just tell you what should be ultimate Gromov-Peterson invariance. Yeah, first you assume that K is algebraically closed. And if K is algebraically closed, then you should fix class of the curve. And the optimal is the following. Consider show group of one-dimensional cycles up to it will be kind of like cycles up to one cycle up to rational equivalence. But then you model out by if finer equivalence, it will be algebraic equivalence. So you can consider two curves connected by sitting in one connected family, which is itself in the curve hygienus. And this is a comfortable dimensional, comfortably generated abelian group. So you get to very fine invariance, and then Gromov-Peterson invariance, I will consider only genus 0. Gromov-Peterson invariance will be something like A and beta. It will be fundamental class of virtual fundamental class of the space of stable masses and mark points of genus 0 plus beta. It will be element of now show some expected dimension of x to the power n with rational efficiency. Because we have orthomorphism, so expected dimension is n plus x minus 3 plus pairing of my class beta is first and class of that example. Yeah, so we got this classes, and already there's something very basic here which we don't understand. For example, we have cubic threefold. Then we scalability our variety of complex numbers. We know the genetic series, it gives them period, mirror one, and so on. So we know these numbers. But we know that in kind of rough sense. We can consider degree of curves as image in topological homology, and even for critic threefold, this group is huge. It's huge. It's not really understood. It's Claire was proved that it's really infinitely generated, and so this numbers of curves on given degree you can decompose in smaller pieces, for which you have absolutely no idea what would be just a color from present and what would be the genetic series. It's big open questions just at the very beginning of mirror symmetry. Yeah, so again, I will not go to the small complicated information. We'll use only kind of rough information on beta. Namely, beta rough will be belongs to Chel 1. But now you mod out by numerical equivalence. Numerical equivalence, it's you count how many intersection numbers in divisors, and this is much simpler story. It's a 3-abelian group, finite one. So we lose torsion here, and that's counting which we are talking about. And finally, it's the plays no role, but if the field is not algebraically closed, then you get just some property of the story. This Maxim beta equals to an beta is compared with the action of for finite group. It goes actually to finite closure level. So this arithmetic property is just property of invariance, nothing else. At the moment. No, covariant. It's a commuting section of Galois. Galois permutes classes of curves and also has some in this way. Okay. Yeah, so that's the whole story, and how we after all this information. So I mentioned the heptagonal multiplicity field of repeated 0. And this ground picture invariance can be encoded and given by Algebraic cycles, and one can keep track of the fact that Algebraic cycles show something called material Galois group. Actually, it was one to material Galois group. What is it? If you have variety, if you have variety and okay, of course we can, because field for 0, we can accept embedded it in the complex numbers. Anyhow, it's not reason to consider only countable genetic fields. So we have variety, and then we have homology. X beta. Variety. I consider the rational vector spaces, rational super vector space. And even one can give this notion of algebraic cycles here, and they're expected to be fixed points at the action of some group, but strictly speaking, we don't know it, and for this, we will develop some tools, even where propose some notion of kind of motivated cycles. It's a certain subspace of Petit homology, and it contains. One can give some one-line definition, but I don't want to do it. Essentially, what is going on? You start with all varieties and images of algebraic cycles. Or you define for a small field, not algebraically closed. But then you have some kind of trouble, just with standard conjecture, where we'll consider diagonal. Is it some of unit components? You add back these unit components, add images of correspondences, and also there is a kind of left theorem. You should add it should be algebraic cycle by left symbol, but if you don't, and you get some big class of homology classes and some motivated cycles, and it's a very easy result of Andreas solves actually doesn't depend on the negative of K2C. It's something absolutely kind of God-given rational vector space, which you can define independently on the basis of K2C. So it has normal algebraic cycles, and what follows from all this sense, it's use only positivity of pairing for primitive classes, that there will be certain a pro-reductive algebraic group over Q, which acts on homology on your variety. And this group actually contains which is mapped to J1. You consider action on H2 of P1, it gives you isomorphism to J1, and it has another J1 which is responsible for action for the given homology. You consider the action of some group on ice model action is very high, and because it's H2, you see here the homomorphism is given multiplication raised square. So this is whole story. And now, sorry, it's not exactly, it's just a map. Just a map. And now we define non-commutative Dollar group. Just G without unfair. It will be kernel of this homomorphism to G1. Oh, by the way, that's what to say. It's central embedding. The central embedding. And from the central embedding, you see that this G contains central G, which is responsible for weight up to mod 2. Yes. So that's the whole story. And it claims that this algebraic cycles, okay, motivated cycles don't to be the same as invariants under this group G. Yeah. Yes. Yeah. So that's a bit abstract. The sense in a complete situation, for example, this simple story which known from 60s, it's Markov K group. You can see the minimal algebraic group defined over Q, such that course decomposition is actual 2C star given course decomposition comes from elements in the classification. Yeah. Okay, yeah, so get this this big group, and what we have here, maybe just one little remark. This group G, it's projected limit of kind of finite dimensional reductive group. It has a group of connected components. It's not epimorphic to its group of connected components. And it has some kind of a connected kernel, which you describe using root systems. But group of connected components is the same as dollar group, is for finite group, dollar group of people. Yeah, so we get this thing that eventually in what I will talk about, we ignore again here again show groups is very complicated infinite rank stuff, but this maps to what? You consider homological of x to the power n, and then you consider invariance under this kind of component, and also it will be covariant with respect to finite groups. Okay. Yeah. Yeah, so that's so the main story is that you get certain probability group with sample Z2. And we have some representation of this group, and we report the whole information in some bunch of templates with some property resources connected component group and little well part. Okay. Now about genetic series. For given zero bound invariance, it's called F0. This should be considered as some functional domain on homology of manifold, and in fact, one should introduce kind of different types of coordinates. First, what you have a variety, you have zero homology, yeah, which is U of U, if its variety is not connected to the finite components of X plus. And this action of dollar stuff. Yeah, you have a zero cohomology, then you get second cohomology of X, which you can decompose canonically in two parts. Namely, you consider an algebraic part. What is it? It's considered chill. This is chill one. It's dual split to the things, to the following things. You consider this classes of curves on 6 up to numerical equivalence, and we take dual space. This will be a great part of. Yeah, so this it will contain this lattice resection of Galois group, so finite representation, and then we got transcendental part. Transcendental part, which everything is pairs zero with example this line balance. Canonical, yeah, because you pair this pairing between curves and sixes on the degenerate. Yeah, so it's canonical decomposition. Here we get Galois projection. Then we get H2 get even common classes of degree 4 and more, and then also we get odd classes. And here we introduce choose the basis of all the spaces. Except algebraic part. And we choose basis. It calls dual coordinates Ti. It will be some parameters of geometric series. And here we for odd variables will be odd remote variables. And for this algebraic part, again, I use the fact that this group is free group of finite one. And it is called Qj, the J from 1 to 1 for this so 1 it will be multiplicative variables responding to be not so what we each curve some class beta will go to a product of some beta j, the j will be some beta numbers. Yeah, and now we take as usual way as a geometric series of problem with invariants. It will be series in Q and T with rational coefficients. So, in T, kind of Laurent series in Q, and in variables Q, in Q variables, monomials like inside some convex cone. And yeah, so you get this at 0, and now I want to see its function on something, and so kind of just phone station. We expect this function should be convergent in complex sense. And convergence in complex sense of all, like the things. So you can imagine that Qi will be close to some actual numbers in C star. And then we get the homomorphisms by logarithm of norms of I goes to max to R. And to have a convergence, we want to all these monomials should go to the numbers with absolute value less than 1. So we get ample column whatever in the group of X. That's U, we get an ample column. We get minus 74, which is due to column of the curves. Column of the curve. Now, in fact, strictly speaking, you get on the rational curves. Okay. All right, so we get this minus sample code, and what is expected that there exists some mysterious domain, which is not exactly this form, but something not conical, but asymptotically this is one domain, such that this if variable Q license is domain and variable T is sufficiently small, then you get convergence. So what you belong to this things and variables T are small. In fact, for this variable T to be small, you don't need all variables T to be small. This H0 and this constant part have no constraints because they unit axiom, I think, appears on them for constant mass, and this will not affect my curve by devices axiom. Yeah, I don't know examples when it's not known. No, it's believed to be true for always, yeah. But again, but we live in kind of hostile world. You shouldn't take it for granted, yeah. And so the way to avoid this singularity, this trouble. Way to avoid is avoid troubles. We replace T and Q by elements of some non-archimedean field. From that we choose algebraically closed field, like use a series of rational exponent, some dummy variable. And this dummy variable you should actually think as a very small positive real number. And well, it's important, it's a way kind of to understand topology, fundamental group. So it's essentially very close to complex numbers. And then what you instead of elements of you start with the elements of T star and you take log of nodes. Now if you literally sit inside the sample cone and nodes of T literally less than 1, then you get absolute eddy convergence. Yeah, it's very cheap. Yeah, so you get we will define canonical domain of convergence. It will be strict interior of temporal cone minus strict interior of temporal cone. Times product of open unit pieces in the T variables, and maybe the full final lines for this dummy variables for which you have no constraint. Yeah, so that is canonical variety of non-archimedean field. And we make a Dirichlet series. Kind of arithmetic properties. I said that this not virtual group acts on this variety. You just extend scalars from Q to this mixture K, acts on this variety, and preserves function at 0. Now, so the action is again a bit tricky. So on this Q variables, the sections will find kind of this representation on J and Z of my Galois group, and on the rest it goes through some finite dimensional factor, the action of the Galois group on two homological line. All right. Yeah, so that this 6 and then over this variety, I don't know what variety, some kind of like Frobenius manifold associated to X. It will be super manifold. Sorry? Oh, so sorry, yeah. With notation is called the Dirichlet series is called F0. Okay. Yeah, and variety called something like BX. will be kind of like Frobenius manifold. So to X. It will be super manifold, yeah, because we have multiple variables. And usually axiomatic of Frobenius manifold, we will get some affine structure. And this will be the application of 6. I'll just keep some non-linear version of Frobenius manifold. It's essentially like F manifold in the sense of Mayer-Hartung, and something which could have a bundle. Have a bundle, namely, we have this manifold, and we multiply, let's say, by a fine line with variable u. And here you can see the bundle, trivial bundle. This fiber will be homological of X. It's now I got always this auxiliary dynamic field. And what we'll have a flat connection to the meromorphic flat connection. And the formula is like this. If you consider derivative with respect to the variable gi, or if the two variables in Q Qj in logarithmic notion, it will be Qji respectively Qj Qj plus U inverse. I didn't really know this basis. The basis is in delta I, and delta J will be basis of the homology. Delta I was multiplication by the J or J. You can see the quantum multiplication at this point of the Frobenius manifold using the subderivative. And similarly, a connection with respect to the U du will be U du plus U inverse and multiplication by some Euler operator. And Euler operator, it will be some function is very simple. Homology on Frobenius manifold is very simple. You use first check plus tangent bundle plus sum over I, degree I is delta I is not 2, degree of delta I minus 2 over 2 multiplied by gi delta I. Then the scale in non-degree 2 over pluses. Yeah, so we got this connection, which is flat, and we see that it has first order pole in U, if you go in horizontal variables, and second order pole, if you go in variable U. Yeah, so that is and bundle and sorry? Grid. Plus gradient operator. So it's gradient operator. Yeah, you're right. Yeah. Gradient operator. It's on H. J will be J minus dimension of manifold. Maybe divided by 2. That's it. Yeah, you're right. Yeah, so that this flat connection. And yeah, here you use actual element of F fine line, but one can make a different version because we are on our opinionated field. We can treat our own as a small number, not necessarily big one, and or even formal variable. And this F bundles has a following structure. This which we have an ugly name maximal bundle. what is the geometry of this space? You get some supermanifold, analytic formal, whatever. Yes. Analytic can get more fine line, make it formal, one and get this bundle disconnection. Then from this story you get automatically the following thing. If you consider this coefficients of first order of this connection along U, then you see the tangent space of U that maps to endomorphisms of the fiber point E0. But this configuration is a commutative operators. And this is one of those maximal, which is as follows. It's maximal family of commutative operators. It says that it's unital assorted algebra, assorted commutative, super commutative algebra. And this is free one model. So it's equivalent that this is cyclic vector. So apply this cyclic vector and identify these values. This case. And yeah, that's situation called invariance. And then I consider this operator coefficients of the whole, it will be still some operator coming to this, so it will be this gives some operator coming to this operator, so it gives a unique element of the solver, it will be some vector field, it's called early vector field, which is a local coordinates exactly like this. Coefficients of minus term in gives early vector field. And then we got rate of multiplication by early vector field at each point. Now, this operator has the following property. It has a general property. If you get finite dimensional supercommutative algebra and run one free module, you get even element of your algebra, you get operated in this model, and then you get spectrum. Because I have my algebraically closed field, spectrum will be subset of this set. And so what we see is important. For any point of this even part of my B, I get the finite subset of A, and then the spectrum of this earlier operator. And the spectrum, first of all, claim the spectrum on odd part. On all parts, you also get the same numbers. It's the subset of I can go from even part. And the reason is the following. You have your element, and this eigenvalues of the things gives you the composition. You can make certain polynomials of the element which will be projected. This one term of the spectrum. And so it means that you decompose your algebra, have family of commutative projectors. So your algebra is decomposed in some of subalgebras, but all subalgebras will be unital subalgebras, particularly if which element of the spectrum this eigenspace will be contain non-trivial even part unit of this, namely this image of the projector. So you decompose your algebra into the direct sum. And yeah, so the fixed point be in even, then we get spectrum. And let's cover by several, decompose in several groups. Like, for example, choose some disk because we're not really good and we go distant. Let's write its union of some pieces, some pieces, some finite different union of pieces. Then if you write a little bit your point on your Frobenius manifold, the second values move a little bit. They move a little bit, and but still, because if you assume that there are some open domains in the velocity, you can still attach decompose pieces labeled by the same set. So what you see here, the tangent space, tangent bundle, maybe canonically splits of certain subspaces corresponding to the second values. And then it's very easy to prove that what you get family of Hermitian population. Get a family of Hermitian populations, supersense. And so and then it implies that the neighborhood of B will be canonically a isomorphic product of neighborhoods of some points in some smaller maximal bundle objects, which not necessarily come from coefficient invariance for some individual pieces, but then we get canonical product. Yeah, that's basic geometry. And now what one can see. What one can try to look on the interaction of this moving spectrum and action of material Galois group. Now consider J invariant J fixed locus. Yeah. Because D contains Z-mod 2, it will be automatically an even part, and it will be smooth analytic variety. Okay. Which really looks locally like a vector subspace in a high structure. So what is the dimension of this guy? Dimension of the space will be dimension of this fixed locus will be rank of G invariant part of cohomology objects. It will be exactly correspond to this algebraic cycles on defined by my small non-algebraic recipe. Yeah, so one can look carefully, especially on H2, on H02. Yeah. And you get subcores on H2 and subspace in H02. Okay, so I get this. Smooth analytic variety. It's obviously connected. Because what you do is it will be some domain in the torus and domain in the vector space. It's connected variety, and then we have constructible function. On this thing, G, with values in the non-negative, it's the number of distinct eigenvalues of the Euler operator. In fact, this very operator, I told you, there can very sloshly, which you can do, you can consider action on all cohomology of X. You consider action on even cohomology of X, or you consider action on the great part of homology of X. 6 great values of seconds. And the claims it will be the same eigenvalues, doesn't matter which of them. And or maybe the breakup will be considered connected, events in the connected components. Because what you do, you have eigenspaces will be it will be subalgebras with unit, and in particular they have this invariant vector subunit for extension. Yeah, so it's you get this constructible function, and then it takes kind of one, because on connect right it has one maximal value to generate point, yeah, and it has open locus from open locus. It is constant. It's constant, and so it means that you should from this fixed locus you remove some discriminant to get finite and modified cover. Finite modified cover of this fixed locus B G minus discriminant. And now we take set of connected components of this guy. You get some finite set, which I call atoms associated to my variety. It's a finite set. Yeah, one can go without this trouble, you remove discriminant, namely you consider ramified cover given by eigenvalues, so consider irreducible components of this variety. It will be the same set of atoms. Yeah, so that's a finite set. And what we see is that if we consider generic point of my fixed locus near in the neighborhood of this fixed points, my variety is the strings product of atoms. And then and then we get some of these germs of, again, this maximal of bundles labeled by atoms. And these atoms are kind of key notion to application to variable geometry. Thanks to what result. What was on? Suppose your variety contains some smooth closed variety. Variety of 4-dimension R. Of 4-dimension R. One can do the following things. One construct two variety. One called X prime, which will blow up X with central Z. Another is X double prime. It will be X and the joint union of R minus 1 copies of Z. It will be this kind varieties. What is nice about them is commode of X prime, which is a more commode of X double prime has G modules. So we get about fits, we can identify commode by some of great correspondences. And corner of Irritanian theorem is that certain connected non-empty domain in Frobenius manifold, so to X prime. It's actually neighborhood of connected domain in its locus. Yes, also compatible with actual color is identified with same things in V of X double prime. Yeah, so this Frobenius manifold have kind of common part. As non-linear varieties, we can identify the varieties as basis as F bundles. Bundles is endowed with G action.
So what is required in order to?
Sorry?
So what is required in order to take the final results as written?
Yeah. No, the reason it's the whole it's kind of construction is canonical, and because of this action of here and there, that is constructed results action on G. It's really nothing. Yeah. Now there's a little bit of massaging which you have to do. Yeah, actually, like 4 years ago, when it was last time in Miami, I proposed a exact formulation of which point should go to which point. It was some kind of limiting point. It was a limiting point, and this is not exactly point of the space. It was not exactly ample plus, and so on. But there is action of kind of normalization book, like explanation of Euler field. And by this Euler field, you can move it easily inside the point of convergence. So this boundary points can go inside, and some has to be really well defined. And what really goes on here? You can see the point in Frobenius manifold for X prime, which is it should be given by some ample plus. I'll take not exactly ample plus. I consider ample plus will be pullback of ample plus on X. In block, yeah, and add some for some small epsilon first chain plus on this. And then it will be ample, yeah. And this first chain plus is really this one is section of the color group. Yeah, so I take this point in terms and maybe zero variables in other things, and then I calculate eigenvalues of my Euler field. I get and this picture. I get something values very close to 1, close to 0, and this control of X, and then I get many values close to the scale root of 1, and then this control of Z, and just as natural guesses, what you see, it will be very kind of attractive central point spectrum for the field for X and Z, and you get product of this manifold. Now it's and that's a theorem, and by this in this way you identify some atoms from some varieties with some atoms from other varieties, because you get all this gives some you have this connected components for X, and you identify some components of X and X prime and X and Z. So you get this identification. This is also analogous result for projective bundles. Also, it's a projective bundle utilization of vector bundle you get the same picture without infinity, and what you get equivalence relation on unit space of all varieties x, atoms of x, generated by this block formula and projected pattern, and to consider quotient space. It's called atoms associated to the field. Now, this notion really depends on the kind of local atoms of variety. Depends on can change if you change the field of definition. You go from non-breaker also non-breaker also. The reason is the following: you allow to variety. The field flow became larger in some larger vector subspace, and then the number of eigenvalues to generate became larger. So this really depends on arithmetic. And what follows? So the set of atoms is kind of some huge set, and it's featured by minimal dimension of x, where this atom can appear. Each atom can appear from various varieties by this whole relation. So it's filtered by this relation, and
The only equivalence relation is blow-up velocity.
sorry,
The only relation is blow-up velocity.
blow and smooth centers and projected bundles.
And projected.
Yeah, projected bundles. Yeah, in fact, projected bundles for this story it's not relevant, but it's convenient to edit. Yeah. Let's just zoom out on the blocks. Consider this illustration. It's filtered by dimension, and then we get abstraction to rationality. If dimension of x is m, and one of atoms, at least one of atoms, coming from x for x does not come from some variety six, some variety w is dimension at most n minus 2, then x is not rational. Because after this, because we make block and block on the set of dimension 2 and more, and so the thing which happens. Yeah, that's a basic principle, and as I explained already 2 years ago, but a bit more complicated sense, the proofs kind of things which people consider as a great result, that generate fourfold cubic fourfold is not rational. And now it's zero. But now we also have some examples which explain next time this non-algebraic closed field. We can this is really I'll explain how to play this game. At the moment we have very simple invariants of atoms to guarantee that these things don't come from like surfaces of course. So at the moment the story goes up in dimension 4, we have plenty of 3 and 4-dimensional varieties of a non-algebraic closed field, for which you can prove they are not rational. So this technology which I explained